All right, welcome to another episode of the Base-12 Book Club, where I'm talking about the contents of my book. Just look at it. What was the book I wrote again? Understanding Base-12 Math, How to Draw the Perfect Circle Using Dawsonal Geometry. So in this video, I'm going to be answering some questions that have been put to me by people who are reading the book. Namely, can we come up with a more articulate proof for the perfect balance of this diagram? Namely, the first ring of the diagram. So I'm talking about the diagram for 360 degrees that I'm showing you how to build, and then from that we keep dividing the circle farther and farther. And another conversation that I'm having on another comment feed is, again, just talking about, can you prove that there actually is a difference between base 10 and base 12? So the crux comes down to, is there a difference between the base 10 Cartesian plane and the base 12 Cartesian plane? Or is there a difference in the geometry that we can perform on the base 10 or base 12 Cartesian plane? So a lot of the times people say, well, you're just working in twelfths, and twelfths are completely accessible from a base 10 perspective. And so that's what we're going to do in this video. I'm going to introduce you again to the geometry of the base 12 dodecagon. We're going to look at it from a base 10 perspective and then go into base 12, do geometry on the base 12 Cartesian plane. We're going to build the first ring of the diagram and really look closely at the proportions and all the the lengths of the various lines and the radiuses of the circles, and really articulate the proof that it does all line up. And then we're going to compare again between base 10 and base 12, what the angles are within that diagram, and that's going to be this video. So let's get started. So first of all, we're talking about a very simple diagram to draw, and it's very easy and precise to draw it correctly because it's defined by specific lattice points that you can. I'm going to start with just on a piece of graph paper. So we'll start with a piece of graph paper. Let's draw our X and Y axis. Then I'm going to describe to you right now which points we use. So starting from the center of our cross, we're just going to count along the X axis the length of 13 little squares and make a point. Then we're going to back up 1 to 12, and then we're going to go up 7, make a point, and go down 7 and make a point. So we're going to do that in all four directions. We're going to do negative X, up on the Y, down. You can see what that looks like. So that gives us 12 points that are specifically defined by the points where the horizontal and vertical lines of the grid cross each other. Those are called lattice points, and now we simply connect the dots. So the first thing that we're going to do is just approach this like we would normally if someone just gave us that pattern on a piece of paper and we assume that we were doing it from a base 10 perspective. So we would draw lines that define the length of 1, and then we would see that, okay, all of these sections of this dodecagon, this 12-sided shape, we would be able to calculate that they're all the length of 0.5 root 2. So I'm going to let you do that calculation yourself. So we see we have 12 lengths that are all 0.5 root 2. So 0.5 is half of 1. So we have 12 half lengths. That gives us 6 lengths of the square root of 2. So the total perimeter of this dodecagon on a base 10 Cartesian plane is the length of 6 root 2. So it's all in lengths of the square root of 2. So now if we wanted to say, okay, what does it look like in the base 12 Cartesian plane? What's the difference between base 10 and base 12? Well, here's the difference right here. We're dividing our length of 1 into twelfths instead of tenths. So we have the same length of 1, but on the bottom here you can see we've divided into tenths, and on the top these are smaller sections and there's 12. So if you think about it, a twelfth is a smaller unit than a tenth. So the base 12 Cartesian plane, when we look at them side by side, we can see it has a denser grid pattern. There's essentially more lines, more horizontal and vertical lines. So there's more lattice points on that Cartesian plane. And actually you can see here the two Cartesian planes are laid on top of each other, and you can see that there's a lot of points that line up in different locations. So some of those points are the same. If we go to the center point, we can see that 0.5 in base 10 is 0.6 in base 12. That's exactly equal. 0.3 in base, I'm going to turn on this actually. 0.3 in base 12 is 2.5. There we go. In base 12 is 2.6 or 2.5 right? No, that's a quarter. Sorry, 2.25, 2.5. Sometimes it's a little confusing going back and forth in base 10 and base 12, but I think you get the idea that some points, yeah, it's 2, 3 is 2.5, right? Of course, 2.55, it's a quarter. So 0.3 is a quarter in base 12. 0.4 is a third in base 12. So some of the numbers don't quite add up the same. A quarter or a third in base 10 is 3.333 or 0.333. We're going to be working with the length of 0.5 root 2. This is a foundational aspect. And so when we try to find 5/12ths, the result that we get is a repeating decimal. So that goes for the 7, also 7/12ths. So 7/12ths and 5/12ths are key lengths in the creation of our diagram. And so we just want to be aware that those points don't line up so perfectly where we just say, well, it's exactly the same. It's a little bit of a question when you get a repeating decimal. How accurate is that compared to a decimal that's not repeating? So we'll just leave that for now, but at least we're aware that we're going to be working in units of 0.5 root 2 and the length of 0.7, the length of 0.5 twelfths on the base 12 Cartesian plane. So that's what we're going to do now. We're going to compare the same dodecagon on the base 12 Cartesian plane. So when we draw it on graph paper, it looks exactly the same, and all that we do is shift where the line that defines the 1 is. We actually make a square that looks larger. So again, remember, the length of 1 is the same size, and the reason it looks larger on our graph paper is because we're not changing the actual size of the decimal place. We're not, because it's on graph paper, these are the same size, so we're ending up with a larger looking square, a length of 1. So, but when we calculate the length of the total perimeter of this dodecagon, we're talking 5/12ths now. So 5 times 12 is 60. So that's 60/12ths, and then 60 divided by 12 gives us 5 again. So now the total perimeter of the base 12 dodecagon is 5 root 2. So that's obviously a shorter length. And so here's a picture where we have the two versions of the dodecagon are next to each other, and you can see that the base 12 version is a smaller version. Again, it's very straightforward when you realize it. The length of 0.5 in base 12 is a shorter distance than the length of 0.5 in base 6. So there's 0.5 in base 10, I should say, is half. 0.5 in base 12 isn't half, it's a little bit less. Okay, so let's look at this pattern a little more carefully. What I want you to know most about it is that it's not just a singular, one-off pattern, but it's actually a repeating pattern. So here's a picture. You can see it has actual rings, and then the second ring of this pattern is built in units that are 2 times that of the first. So this first pattern, the sections are in length of 0.5 root 2. The second ring, each side has the length of 2 times 0.5 root 2, or let's say 10/12ths. The third ring is in 3 times 0.5 root 2, which is 15/12ths. And then the fourth ring is the lengths are 20/12ths, 4 times. And that pattern just keeps going and going and going. So we're going to be going to the fourth ring of the dodecagon, and that's where we're going to be manipulating those lengths, working with that same precise length of the perimeter. And we want to change the arrangement of the dodecagon to become a perfectly, a regular dodecagon. So that's a dodecagon where all of the points are equidistant from the center. So you might notice when you look at this one, you can see it's not a regular dodecagon. It's an irregular dodecagon, although all the sides are the same length. Okay, so you can check that and prove that to yourself. So we want to see how we can manipulate the sides and make it a perfectly regular dodecagon. So the first thing that we need to do, or what we want to do, is look at this geometry, at this shape's relationship to the 30-degree line. So this is a little detail that's very important, because it looks like, if you look at it close at that line, I'm going to draw a line from the center point through the point that defines, one of the points that defines the shape of the dodecagon, so we create a triangle. So remember, we went over the length of 12 and then up 0.7. So in base 12, that's the length of 1 and then up 0.7. So we're creating a triangle that has a base of 1 on one side of the right angle, goes up the length of 0.7, and then we have our hypotenuse. So when we square 0.7, or 7/12, in base 12, 0.7 times 0.7 gives us an answer of 0.41. Okay, so that's the base 12. I'm gonna have to do that in base 12 because I don't know what the fraction is, squaring and the square root and all that. So let's just say you can see that makes sense. You know, you can sort of figure out that number. That's a base 12 number, and we have a base of 1, a height of square root of 0.41, and then that gives us a hypotenuse of the square root of 1.41. So now what we want to do is compare that to the special right triangle, which has the length, or the inside degrees. We call it a 30, 60, 90 triangle, where those are the angles on the inside. The base is the length of the square root of 3, the height is the length of 1, and then the hypotenuse is the length of 2. So what we want to do is change the proportions of that, or not the proportions, but we want to change so that the length of the base is also the length of 1. So we do that simply by dividing by the square root of 3. So square root of 3 divided by the square root of 3 is 1. Then 1 divided by the square root of 3. Remember, 1 divided by 3 in base 12 is 0.4. Okay, remember that. So 1 gives us the length of 0.4. So the square root of 0.4. And then the hypotenuse of this triangle is the square root of 1.4. So we can see now when we compare, we have 0.41 and 0.4. So what this shows us is that the line that's defining that triangle that's defined by the points that define the dodecagon is a little bit higher. So that when we connect the 2 points on either side of the 45-degree line for that angle there, that corner of the dodecagon, that line that is perpendicular to the 45-degree line is floating between the 30 and 60-degree lines. It doesn't go all the way to reach them. It's a little bit inside. There's a gap between the length of that line and the lines that define the 30 and 60-degree lines. So we can kind of zoom in there and see that gap. It's very important to realize that that gap exists, and that this over 1 up 0.7 is not a 30-degree line. It's a little bit more. Okay, so that's going to be something that we pay attention to. So now we're going to go to the 4th ring of the dodecagon, where the proportions are all exactly the same, and we are going to draw some circles that are based on the lengths of, or that are based on the lattice points that are around the 45-degree line. We're using the 45-degree line that's in units of square root of 2 because we want the diameter of our circle, or the diameter of our dodecagon, to be in the same units as its perimeter. So the perimeter is in units of square root of 2, and the diameter, I'm going to call that line, the 45-degree line, the diameter of this pattern, the dodecagon. We're working in units of square root of 2. So let's go over the length of the length of the line that's in units of square root of 2. Let's go back actually to the first ring of the diagram. I haven't given you that length yet. So here's a picture, and you can see all these numbers here. This is from my book, and all the numbers are linked to the coordinates of the dodecagon. But the main one is what you see here, the length of 0.96 root 2. So that's the length of the 45-degree line, starting at the center point to the point where it's crossing or intersecting the corner of the dodecagon that's perpendicular. So those two lines are perpendicular to each other. 0.96 root 2. So as a fraction in base 12, it's not 0.96 1/44. We multiply 9 by 12. Those first 9 sections are each going to be in 12ths now. So 9 times 12, I think, is 108. And then we add, so that's 108 1/44. And then we add 6 144ths. So we got 114 1/44 for the length of that line from a base 10 perspective using the fraction. So now we're going to multiply that by 4. Okay, so go back to 0.96 times 4 is 3.2 root 2. So that's the length of the 45-degree line when we get to the 4th ring of the dodecagon. Okay, so that's going to be the radius of a circle. We're going to draw a circle the length of 3.2 root 2. And again, you can do the equation there where you multiply 114 times 4, and you divide it by 144, you're going to get 38. So that's 12 goes into 38 3 times, and 2/12 left over. 36, 2/12 left over. Okay, so it's all the same. So if you're thinking it's just in twelfths, you're right. It's easy for us to access all these points using base 10, using twelfths and 1/44ths. At this point in the diagram, we don't need to go any deeper into the Cartesian plane than 2 decimal places. Okay, so what we're going to do is draw a circle with the radius of 3.2 root 2. So this is what that looks like. And then we're going to draw another circle, and we're going to draw a slightly larger circle. We're going to use the points on the perimeter of the dodecagon. We're going to travel along that dodecagon perimeter the length of 0.5 root 2, one section of our length. Remember, we're working in units of 0.5 root 2, so we're going to go over 5/12 along, again, another lattice point, and we're going to draw a second circle. So now we have basically 2 circles that are defined by the points on the 4th ring of our dodecagon pattern. So now what we want to do is we want to make some points on those circles around the 15-degree line so that we can have the same relationship to the 45-degree line with those points. What I'll do is accentuate that line. So we have a line, so we've got in both directions from the 45-degree line in both directions, and we have 2 lattice points, and so the distance between those 2 points is a distance of 2 times 0.5, which is, I'm going to say 10/12. Okay, and so we do that on all 4 corners. So we have 4 sections of line that are all the length of 10/12, and what we want to do is, and they're all balanced on the the 45, and then the equivalent as we go around the circle or around the pattern. And we want to generate like a 15-degree line and a 75-degree line, and create that same geometry using the 2 circles that we just drew. So how do we do that? How do we get those other degree lines? So now we have to introduce another geometric pattern. I'm sure most of you are familiar with this. I call this the Dawson-Pisces diagram because it does divide the circle into 12 and 24 sections. So there's a base 12 element to it. But this will be our axiom that this pattern does divide the circle perfectly. I'm not going to go into proving it, but it's a given. Although it's very difficult to find this pattern in any sort of modern math textbook, we're going to use it. I do show you how to build this pattern or draw it in the book. You simply take a circle of a certain radius, doesn't matter how big, but once you've drawn your first circle, you put your compass on the perimeter or the circumference. You put your circle on the circumference of that first circle, draw another circle, and then where that circle is crossing the circumference or the circumferences intersect each other, you put your compass on that point. You keep drawing circles and go around. You draw your X and Y lines defined by those overlapping points, and then you do the process again. You get this diagram. It's very easy, and this diagram divides the circle perfectly into 24 equal sections. So this is the backbone for the diagram for 360 degrees, and it's also the geometry that we need to begin this process of converting the irregular dodecagon into a regular dodecagon. So we draw that pattern. Now we're going to focus on the 15-degree line where it is crossing the radiuses or the 2 circles with the radius of 3.2 root 2, and then the slightly larger one. I'm not even going to, well, I can show you here. I'll give you, you could just sort of look there and see the math. We don't really need to know the radius of that circle. It's easy to calculate, but just in terms of the logic of the geometry, what we're going to do is set our compass to the length of 0.5 root 2. Again, the same distance from where the 45-degree line is crossing that inner circle. We use those very specific lattice points to set our compass. Then we place it on the 15-degree line where it's crossing that inner circle. Then we make marks on the outer circle. So now the points, those 2 points on the outer circle, if we draw a line between them, that line is also going to be the length of 10/12. Okay, so now this is what that looks like. So now we have 12 sections of line that are all the same distance from each other. So we have the 15 degree line, the 45 degree line, the 75 degree line, and then the same in the other 4 quadrants of the Cartesian plane. How long, what's the total length of all those lines? So that's basically 10 twelfths times 12. So 10 times 12 is 120. I'm going to have to write this down. Just remember what is 120 twelfths. Okay? So what's the total length of our 4th ring of the dodecagon pattern? Well, we know that the first length was 5, so we get times 4 is 20. So 200, is that right? It's 20 twelfths, and then times 12, 20 twelfths times 12, 20 times 12 is 240. There we go, 240. So the total length of our base 12 dodecagon is 240 twelfths, root 2. Okay? So when we add up all these lines here, those sections, we have 120 twelfths. So that's exactly half of the total amount of our dodecagon perimeter. And so you can see the pattern here. What happens if we just connect the points that we already have? We're not going to draw any more points. We don't have to make any more marks on either one of those circles. All we need to do is draw or connect the same points, but where the gaps are. So there's 12 more gaps. So when we do that, we should get the same length of 120 twelfths. So when we add the first series of sections of 120 to the second series at 240 twelfths, which is exactly the same length of the dodecagon. So is this all perfect? Does this line up? Is everything equal here? So I've been trying to, this is where I wanted to answer the question that can we articulate what just happened in a way that sounds very sort of math professional. And I'd say like one of the things is simply we can draw 2 circles that have a larger gap between them by using the end points of the dodecagon. Okay, I decided to point out one more thing or give you a little bit more information about the arrangement or the relationship of the point where the 45 degree line is crossing the dodecagon to circles that could be drawn by its sort of outermost points and then the innermost points that are on the x and y axis. So we go back to the first ring of the diagram. Remember, it doesn't really matter because all the dodecagons have the same proportions, but here's a diagram where I've drawn 3 circles. One is the outer ring defined by the farthest, sort of the point farthest from the center, then the inner ring, which is the point on the x and y axis, which is closest to the center, and then the middle point, which is the point that's defined by the 45 degree line. So I'm going to give you the radiuses of these 3 circles. The outer circle has a radius of the square root of 1.41. The inner circle has a radius of the square root of 1.21. And then the middle circle has a radius of 1.306. Again, all units 1.306 root 2. Well, no, sorry, not root 2. It's just that when you do it, it's in units of square root of 2, but still it works out to 1.306. So you can see those here. So it's almost 1.21, 1.31, 1.41. So that middle ring is essentially perfectly in between those two other rings, so that the lines that define the dodecagon sort of go out to one ring that cuts back into the next one and sort of zigzags its way through those 2 rings. And the reason I wanted to show you that is that the same proportions are for each ring. So the 4th ring that we were just working on, the polygon that we drew is falls between. We're using the same radius, the same point in relation to the overall length of the dodecagon is the point where the 45 degree line is crossing the dodecagon. So that's our anchor for the polygon that we just drew, the 24-sided polygon. So my first statement would be, given that we're using the radius of the initial dodecagon pattern. That initial pattern allows for the unbroken perimeter of the 12-sided dodecagon or polygon. Given that we're using the same radius, the 24-sided polygon is basically, we're trying to see, are all the lengths touching each other, and is that radius consistent? Is there any part of this diagram where there's going to be a gap where the lines don't quite reach, or whether it's sort of lopsided one way or the other? That's the question that we're trying to answer. So the 24-sided polygon remains well within the bounds of the original dodecagon. It's sandwiched between the two. There's nothing, no part of it sort of sticking out. The total length of all the line segments is, the initial division was exactly half of the total lines. When you add up all those lengths, it adds up. The space, so that space that I was talking about, when we look at the dodecagon, when we carry those lines straight, we saw that there was a gap on either side of the 30-degree line. So that enables us to do the action of connecting those dots. And in a way, those two sections, again, of 0.5 root 2 with a gap between them, can close. If you sort of imagine a movement happening, again, although there's no movement happening, we're simply connecting 2 points. But in the geometry, we can see how we had the space to do that. If the initial dodecagon, the very first version, if that line went all the way to the 30-degree line, there would be no room for it to close again. So we're using half of the dodecagon to sort of go away or out in the form of the right angle, and then the other half section to close back in again. And then just the fact that we're working off of the 15-degree line, and so its relationship to the 45-degree line, that's a 30-degree section, 30-degree section to the, each of the sections that we're working with are 30 degrees from each other precisely. So anything we do on one degree line is being mirrored by the other. So the space between them, it's always exactly, the 30, 60, 90 degree, the X and Y axis. So I think that's it. So I put forth that this is a perfectly balanced geometric pattern where it's completely balanced around the the 15, 30, 45 degree, the division of the circle by our Dawson-Pisces diagram. It's anchored onto the base-12 Cartesian plane. So what that says, when we look at this, we look at the triangles. We've created 24 triangles. And each of those triangles have a base. These are isosceles triangles. They have a base of 5 or 10 twelfths. Okay, and then that center line is the length of 3 and 2 twelfths. So that's a 15-degree section. So if we cut that triangle right down the middle, we got two triangles that have their angle theta. And it is half of 15, which is 7.5 degrees. So let's look at that triangle right here. So we have a triangle, one side of the right angle is the length of 3 and 2 twelfths. The short side is the length of 5 twelfths. We don't really need to know the hypotenuse. We're gonna use some trigonometry now. Because we're still in base 10. Using twelfths, we're still in base 10. We can say, okay, what's the angle if we went to our calculator and figured that out? So what we would have to do is we would change those into decimals. So when we figure out 0.5 or 5 twelfths, we divide 5 by 12. And if I remember correctly, we get, remember now, 5 divided by 12 is 0.416666 repeater. And then 2 divided by 12, which is like 1 divided by 6, is 0.1666 repeating. Okay, so we convert. So we'll start with the 5 twelfths. So that's 0.41666. So what we do is we go to our calculator. We get with our sine, cosine, tan. Now we're doing some trigonometry. We want to find the inverse tan. So the opposite, which is the 0.5, over the adjacent, which is the 3 and 2 twelfths. So we do 0.416 over 3.166. Both of those are repeating. So what we're going to do is we're going to go 0.416, so just 3 decimal places. and then 3.166. Okay, and then we're gonna do that calculation, and we get an answer of 0.131396083. So then we hit inverse tan on our calculator, and we get an answer that's 7.485558347. Okay, so then we're going to do that equation again, but now I go as many decimal places as I can in my calculator. So I got about 9 decimals, so 0.41666 9 times all the way to max out my display screen, divided by 3.166 as many decimal places, and I get a number that's very similar but not quite the same, 0.131578947. And so when I do, inverse tan, I get 7.495857619. So we get closer to 7.5, which is 7.5 in base 10, but we don't quite get there. So if someone was to ask, if this was a question on a math test, what's theta in a triangle where it's 5/12 with those exact proportions, the answer is going to be like 7.499, something. So it's not 7.5 degrees. That's the answer in base 10. So which is it? We did the geometry with literally 1 decimal place, 3.2, 0.5 on the base 12 Cartesian plane. So we're anchored in twelfths. So if we were now to sort of take that base 12, now that we've drawn the diagram, we've inked it out on let's say our computer screen. If we were to slide out the base 12 Cartesian plane and slide in the base 10, that's kind of what we do when we start to do this, when we do the switching over, when we start to divide, 5 by 12 and 3, that's a base 10 calculation. If we stayed in base 12, we just have 0.5 and that's it. And whatever calculation the calculator is doing, we would do it in base 12. And that's where I haven't been able to go that far. I've asked people, I say, what's the calculator actually doing when we put in those numbers? And I haven't got a good answer yet. I haven't been able to figure that out. I don't know enough high-level mathematicians to really answer that question for me. What algorithm or what process is it doing to get those numbers? So I would like to know that, because as far as a geometric pattern, I can't see anything wrong with it. So I'm going to leave the video here. We're just the creation of this polygon. Was there any point where it felt? Is there any logic in that diagram in twelfths where we haven't created the division of the circle into 7.5 degrees perfectly? Okay, and I know that in my book, actually, I approach it differently. I divide it already and just say it works out, because I've gone through this process before and I felt it was kind of obvious in a way, but at the same time, this is what proofs are all about, is really meticulously going into the details. So that's the difference between base 10 and base 12. In base 12, it would just stay 0.5, it goes 3.2, and then we would just, units of root 2, and we would just leave it. We'd accept the geometry and move on. The entire diagram for 360 degrees and the implications that this is actually a precise triangle and gives us 7.5 degrees is huge. 7.5 is, half of 15. Those proportions suddenly opens up the geometry of this diagram. It's a foundational aspect of geometry. The fact that the dodecagon is a triangle where you go over 1 and then up 0.7. That length of 1 anchors again that triangle onto the Cartesian plane, the same way that the 45-degree triangle where you have sides 1, 1, square root of 2, and the special right triangle where it's square root of 3, 1, and square root of 4. Any triangle that has the length of 1 is a foundational aspect. Any geometry that uses the length of 1 permeates all of geometry, because you can work with those proportions. So working in twelfths gives us access to this geometry. So that's it for this video. I hope you liked it. I want to hear your comments. What do you think? That's the difference between base 10 and base 12. In the next video, I'm going to start up here. I'm going to show you how we go through the process of dividing the diameter into the circumference with a gap, and that gives rise to a version of pi, the diagram. We're going to go into how to build it. If you are curious, it's basically a week before Christmas. I don't know if I'm going to get into that video until the new year. I got a lot of things coming up, but you can buy the book and get ahead of the game. I show you the version of pi. There's patterns in there. This is the thing. There's all these patterns. One pattern I noticed, just the basic, simple version of pi that emerges. I almost don't want to say it if you're new to this, but because it scares people away, because pi is so foundational, so fundamental, and held in such high esteem that if you say, well, actually, it's wrong in base 10, people just shut down right away. But there's an interesting pattern there. If you take the first three numbers and add them to the second three, you get something going on. So for those of you who are, if you're still with me and you're watching this, play around with those numbers. There's more patterns in there. And then also, let's start exploring sine, cosine, tan with the version of pi. This is the next level also. Can you calculate some of the numbers that emerge from that geometry using the base 12 information I've given you? So you have all the information you need. You can, again, draw this on graph paper. The challenge is that we don't have any computer programs in base 12 geometry. So when people say, oh, it's just in base 12, you can see now why it's important. If you're still looking for Christmas presents, go to my other website, ericlarsonart.com. There's base 12 merchandise there, Dozenal merchandise, shirts and sandals and notebooks, all this kind of stuff in base 12 with some of the geometry that I've been creating. And everybody have a Merry Christmas. Wish you the best, and I hope to see you back here in the new year. Thanks for watching.